Hello and welcome to Engineers Mindset Academy. So today we are going to be looking at a particular assignment which I received from Jigjiga University all the way from Ethiopia. I believe this is on solid mechanics or what you call strength of materials. Let's look at the question. The question says, for the system of the beam, pin supported at end A and cable supported at end B, a force P is applied at L1 distance from A and the cable has a length of L as shown. A vertical member is found directly below B with clear distance delta. The first question says, determine the normal force in the cable. Second question says, determine the safe diameter of the rod B that is holding the cable if the allowable shear stress is 100 megapascal. The third question says, at what temperature will NB touch the vertical member? The fourth question says, specify the location of the maximum flexural strength. And the final question says, determine the maximum flexural tensile stress in the beam. All right, so we're given this beam, and then you're given these parameters. Take Young modulus to be 200 gigapascal. You have delta to be 5 centimeter. You have T1 to be 25 degrees Celsius. You have L1 to be 2.4 meters. You have L2 to be 3.5 meters. And you have L to be 2.6 meters. Now, in this case, L stands for the length of the cable. Okay, keeping that in mind. Whereas delta stands for the spacing or the gap between the vertical member and the beam itself. So this is the beam, pin supported at point A. So there's a pin reaction here or pin support here, and then there is what? Okay, this cable at point B. Then it carries a force P. We were also given the value of the force. Okay, the value of the force P was given to us as 84 kilonewton. P is given as 84 kilonewton. So we're given the value of P also as 84 kilonewton. Now this is the dimension of this beam, okay, with a height of 240 and a width of 110. So which means this beam is a rectangular beam. Okay, it means that the beam is a rectangular beam. All right, having this height and this width. So let's start with the first question. First question says, determine the normal force in the cable. So we have the beam, of course. This is pin supported at A, and we have a cable at point B, cable supported at point B. Of course, this cable is tied at this point, and the force on a cable is always what? Is always directed towards the point where it is tied. So this force is an upward force tied at this particular position. But then again, since they said the condition there says find the normal force simply means that the force must be at 90 degrees towards the surface. So that gives you the normal force. It must be at 90 degrees to the surface. All right, so we start first with the free body diagram. You start by plotting the free body diagram. Free body diagram is simply a diagram of forces showing all the hidden force on a system. So we have this. Now at point A, we have a pin support. And I said for a pin support, we have two reactions. One is vertical and one is horizontal whenever we see a pin support. So since a pin support exists at point A, it means we have two reactions, one vertical and the other horizontal at point A. So call this vertical reaction RAY, which means reaction at A, Y signifies vertical, whereas horizontal becomes RAX. Okay, X there signifies horizontal. We have a point load at C acting vertically downward. So at C, we have a point load, and the value of that point load was given to us. Not forgetting we were given okay, P to be equal to 84 kilonewtons. So we have this value to be 84 kilonewtons. And finally, at point B is where the cable support is, and this cable support is an upward force. Okay, it's a vertical support. So we simply call that this is point B. Let's call the cable support FC, which means force at C. Question says find the cable force at point B. Okay, C stands for cable, sorry. C stands for cable, and of course F stands for the force. So that's the cable force. Distances apart from A to the load, we have L1, and L1 was given as what? 2.4 meters. So we have here to be 2.4 meters. From the load to point B, we have L2 distance, and L2 was given as 3.5 meters. So you put that down, 3.5 meters. So you have this. Okay, this is point C. All right, so that becomes a free body diagram of this system. Now, to find these reactions, we employ our equilibrium laws. What are the equilibrium laws? The first law is summation of all horizontal force, summation F of x is equal to 0, considering all forces pointing to the right to be positive and forces pointing to the left to be negative. And if you look at this beam, only one force points horizontally, and that is what RAX. So this simply means that RAX is equal to 0. Hence, the horizontal reaction at point A automatically becomes 0. The next equilibrium law is summation of vertical forces, summation F of y is equal to 0. So we consider vertically upward force to be positive and vertically downward force to be negative. So we start from beginning of the beam and sum all the vertical forces on the beam, considering upward force to be positive and downward force to be negative. So at A, I have RAY pointing upward, so it's positive. You put it out, RAY. At C, I have 84 kilonewtons force acting downward, so it's negative, minus 84 kilonewtons. And at B, I have the cable force FC pointing upward, so it's positive, simply plus FC. The whole of this is equal to 0. So therefore, okay, just to separate these two. Now, I have that this is an unknown term, RAY. FC is also an unknown term. So let me simply send this value, minus 84, over to this side of the equation. Hence, I have RAY plus FC to now be equal to negative sign, cross and equal to sign becomes positive. So we have what? 84 kilonewtons. Call this equation 1. So you notice that equation 1 involves what? Two unknowns in one equation, which means it is very impossible for us to find the value. So the best thing to do at this point to be able to solve this problem is by what? Considering another equilibrium law, which is what? Taking moment of force about a particular point on the beam. Now, I always tell my students, if you're taking moment of forces, take it about a point on the beam where you have numerous of force. Now, I have at point A two unknown reactions there. So it is best for me to take moment at this point because moment is force times distance, okay? And if moment is force times distance and I'm taking moment at point A, the distances apart from this force and that point is 0 because there's no distance between RAY and point A. There's also no distance between RAX and point A. The two forces exist at point A, which means that distance is what? 0. If they multiply by 0, they automatically become what? 0. All right, so that is the essence of taking moment about that particular point. So we simply take moment at A. So we consider summation of moment from equilibrium law at A to be equal to 0, considering clockwise moment to be positive and anti-clockwise moment to be negative. So you simply have this. So if we are taking moment at point A, then like I said earlier, the moment of these two forces at this point become automatically 0. Now I have to move to the next force, 84 kilonewtons force. This force is pointing downwards, which means the line of action of this force is where coming downwards. Hence, this force will turn about to take moment in this position, making what? A clockwise turning to take moment at point A. And we said let clockwise moment be what? Positive. So which means the moment of this force about point A is positive. And total distance it takes this force to get to point A is what? 2.4 meters. Therefore, we have 84 multiplies 2.4. Next, we have the cable force FC. This force is pointing upward, which means the line of action of this force goes up. That means this force will turn about in this direction to take moment at where? Point A. And if you notice, this direction is what? Anti-clockwise. We said let anti-clockwise mean the what? Negative. And this direction is anti-clockwise. So which means the moment of this force about point A is simply what? A negative moment. And then the total distance it takes this force to get to point A becomes what? 3.5 plus 2.4, which is actually 5.9. Hence, I have minus FC times 5.9, and this is equal to 0. Okay, minus because it's an anti-clockwise moment. So let's expand the bracket now. I have 84 times 2.4 gives me 201.6 minus Okay, this is 5.9 FC, and the whole of this is equal to 0. Alright, so at this point now, I will simply send minus 5.9 FC over to this side of the equation. So I have here 201.6 is now equal to negative sign cross an equal to sign gives us positive value. So I have 5.9 FC. Okay, so in order to make FC subject, it means I have to divide both sides by what? The coefficient of FC, which is 5.9. Therefore, FC becomes now 201.6 divides 5.9. This implies that the cable force FC is now equal to, let's obtain that division, 201.6 divides 5.9. That gives us 34.2 kilonewtons approximately. So the cable force is actually what? 34.2 kilonewtons. So let's keep it down somewhere. FC is equal to 34.2 kilonewtons. This gives us the value of the cable force. So we have this. Now, having found the cable force, we now move straight towards question 2. So I will still wipe this side and solve question 2 over that side. So question 2 says, the second question says, determine the safe diameter of rod B that is holding the cable if allowable shear stress must not exceed 100 megapascal. So we're given allowable shear stress. Okay. Allowable shear stress tau is less than or equal to 100 megapascal. That's a condition. It mustn't exceed 100 megapascal. Okay, so if we have this condition and we are asked to find the diameter, we simply make use of the equation for shear stress. Shear stress, which is tau allowable, is now equal to torque times radius all over J, where J is simply the second polar moment of inertia and T is the torque. Now, the second polar moment of inertia, J, where J is equal to pi diameter to the power of 4 all over 32. So you notice now that there's diameter in the second polar moment of inertia. Hence, all we need to do is to what? Solve for second polar moment of inertia. But then, what is the torque? Torque itself, where the torque itself, T, is equal to force times radius. The torque of every object is simply the force acting on that particular object times the radius arm. Now, the force in this case, we are talking about the rod at B, and the force that existed at B is simply caused by what? The cable force. Okay, so simply the cable force is what exists at point V, which is given as 34.2 kilonewtons, what we've already solved earlier. That means this force is simply what? The cable force multiplied by the radius. But then, what is radius? Radius itself, okay, where radius is always given as diameter all over 2. Radius of every object is given as a diameter all over 2. Okay, so which means we can now rewrite this torque. This simply implies that torque T is equal to the cable force, okay, multiplied by what? Diameter all over 2. This gives us radius. But what is the cable force? We've already solved for the cable force and we obtained 34.2 kilonewtons. So this simply implies that cable force, or sorry, this implies that torque is equal to cable force is 34.2 kilonewtons, okay, multiplied by, okay, kilo means by 10 to the power of 3. Mind you, 34.2 kilo. Kilo simply means by 10 to the power of 3. That's simply saying you're multiplying 34.2 by 1000 newtons. So to convert this to newtons, all right, so multiply by 10 to the power of 3, multiply by diameter all over 2. So this is actually 34.2 by 10 to the power of 3 d divided by 2. So let's obtain that division. This simply implies that torque is now equal to, let's obtain 34.2 by 10 to the power of 3 divided by 2. Okay, that will give you 17.1 by 10 to the power of 3 times the diameter d. So this gives us the value of the torque. We know the torque now. All we need to do is put into this equation and make J subject of the formula. So from shear stress, which is tau, equals C times R all over J. We simply make J subject of the formula. Therefore, we are going to find that J is equal to, it becomes T times radius all over allowable shear stress. Okay, this becomes now your second polar moment of inertia. Simply making J solve formula from this equation, we have the torque times the radius divided by what? The shear stress. Now we know the torque. Once again, radius remains what? Diameter all over 2. So this simply means that this equation cannot be written as, in place of torque is 17.1 by 10 to the power of 3. So we have 17.1 by 10 to the power of 3d multiplied by radius once more is diameter over 2. So multiply by d all over 2 divide by tau. And tau is the allowable shear stress, which was given to us as 100 megapascal. So you have divide by 100. Mega simply means by 10 to the power of 6. So mega simply means by 10 to the power of 6. Okay, so from here, you can find that J is equal to, now let's evaluate the numerator here. This becomes 17.1, sorry, 17.1 by 10 to the power of 3d times d. That gives you what? D squared all over 2. So you have here, okay, let's take it up a bit. Okay, so you have that J is equal to, this becomes 17.1 by 10 to the power of 3. Now observe that D multiplies D gives us D squared all over 2, because we have D squared, D over 2, yes, it becomes D times it becomes D squared all over 2, divide by 100 megapascal. Okay, so divide by 100 by 10 to the power of 6. So this is equal to, now this is what we're going to do. Let's obtain 17.1 divided by 2. Okay, let's obtain 17.1 divided by 2. So that simply gives us 8.55 by 10 to the power of 3 d squared divided by 100 by 10 to the power of 6. Okay, now this is what we are going to do. I want you to keep this in mind. Remember we said that J is equal to what? Pi d4 all over 32. So which means here we have J being equal to this value. Of course, this is equal to J, but we know that J is equal to what? Pi d4 over 32. So we are going to be equating, in place of this J now, we are going to be replacing it with what? This relationship, pi d to the power of 4 divided by 32. All right. So I'm taking this off now. Okay. So in place of J is pi d to the power of 4 all over 32. And this is equal to, now, let's obtain 8.55 exponential 3 divided by 100 exponential 6. That gives us 8.55 by 10 to the power of minus 5 d squared. Now from here, we can easily cross multiply. Let 32 multiply everything here. So we are left with what? Pi d4 on this side of the equation. So this simply implies that, okay, we are left now with pi d to the power of 4 is now equal to, simply cross multiply. 32 multiplies everything here. You have 32 multiplied by 8.55 by 10 to the power of minus 5 d squared. Okay, so therefore you have pi d to the power of 4 is now equal to 32 multiplied by this value. Let's multiply that value by 32. So we have 2.735 by 10 to the power of minus 3 d squared. Okay, so from here, all we need to do now is observe that on the right hand side of the equation, we are seeing d squared, and here we are seeing d4 and pi, and we need diameter. So in order to find diameter, what we'll do is to divide both sides. Okay, divide both sides by pi d squared so that we can be able to eliminate this d squared over here. So we have pi d to the power of 4 equals 2.735 by 10 to the power of minus 3 d squared. So we divide through by pi d squared, we divide through by pi d squared. So you observe that pi cancels pi. Now this is d squared, therefore 2 will cancel 2 of this d4. So I'm left with what? D squared here. On this other side, d squared cancels what? This d squared. So it means that what I have here left is what? D to the power of 2. And that's equal to what I have here now becomes 2.735 by 10 to the power of minus 3 all over pi. And pi is what? 3.142. So this simply implies that d squared is equal to, let's now obtain 2.735 exponential minus 3 divides 3.142. That gives us 8.7046 by 10 to the power of minus 4 approximately. So in order to find d, it means we have to take the square root of this value. Therefore, d is equal to the square root of 8.7046 by 10 to the power of minus 4. Okay, so upon doing this, we are going to find that the diameter of the rod D is now equal to, let's obtain the square root of that value. That gives us approximately 0.030 in meters. Okay, so if you want to convert this to millimeter, you can multiply by 1000 and you have approximately 30 millimeters. So the diameter is simply either 0.030 meters or 30 millimeter. So the third question says, at what temperature will NB touch the vertical member? At what temperature will NB touch the vertical member? Now, I want you to have a picture of something. If NB touch this vertical member, it means the both of them are now in contact, and therefore this will become what? Zero. There is no longer any gap between them. So you have something like this. This is NB. This is NB coming in contact with the vertical member. Hence, there is no gap between them. Therefore, this change or this gap is equal to what? Zero. This deflection is zero because the two members are now what? In contact. Now that brings us to the idea of what? Thermal expansivity or linear expansivity. Recall, from linear expansivity, you have that the change in length of every object is equal to the original length of that object multiplied by the linear expansivity multiplied by change in temperature T2 minus T1, the final temperature minus the initial temperature. And from this question, we were given T1 temperature or the initial temperature to be what? 25 degrees Celsius. It was given in the question. So I said when they touch, when they touch, what happens is that this change in length becomes what? Zero. There is no change in length between them. If these two are in contact, then delta becomes automatically zero. Therefore, this equation becomes what? In place of change in length, you have 0 is equal to, original length of the rod was not given, but it's not a problem. You have L times coefficient of linear expansivity multiplied by T2 minus T1. So what we need to do at this point is expand this bracket. So I have here 0 is equal to L alpha times T2 will give me what? L alpha T2, okay, all right, minus L alpha times T1 will give me L alpha T1. But not forgetting that T1 is what? 25 degrees Celsius. Therefore, we have here, but before then, let's send minus L alpha T1 over to this side of the equation. Negative sign cross and equal to sign will give us what? Positive. Hence, we have L alpha T1 to be equal to what here? L alpha T2. Okay, so now let's observe what happens there. Now, from here, we are looking for what? The temperatures. So we are looking for temperature T2. Divide both sides by what? L alpha. I have here L alpha T1 all over L alpha equals L alpha T2 all over L alpha. So notice that L alpha cancels L alpha cancels L alpha. I have that what? T1 is equal to what? T2. So this simply implies that T2 is equal to T1 remain or was given as 25 degrees Celsius. So it means that the temperature also remains the same when the both of them come in contact. It doesn't change. T1 equals T2 and is given as 25 degrees Celsius. So that's it for the third question. Let's take a look at the fourth question. The fourth question says specify the location of the maximum flexural strength. Specify the location of the maximum flexural strength. Okay. All right. So I'm going to do that over here. All right, to specify the location of the maximum flexural strength, we consider first the section given to us. In this question, this section is a rectangular section, so it was stated clearly here with this diagram. This is a rectangular section of height or depth 240 millimeter and width 110 millimeter. So I converted this to what? To meter by dividing 240 with 1000. So we have 0.2 meters. We also divided 120 here by 1000. We also have 0.11 meters just to convert them to meters. So this is now a rectangular section. The point where the maximum flexural strength occurs is called the neutral axis or neutral point. So this is the neutral point at the middle, and from the top to the middle is the point where what the maximum neutral point occurs. This is neutral point. From the top of the rectangular section to the middle or to the neutral point gives you the point where the maximum flexural strength occurs, and it is simply given as y equal to the depth h all over 2. So this is equal to the depth there was given as 240 millimeter. If you want to solve in millimeter, divide by 2. So this simply means that y max is equal to 240 millimeter divided by 2 will give us 120 millimeter. So this is the point of maximum flexural rigidity. That's where it occurs. And the final question says determine the maximum tensile stress in the beam. We are asked to find the maximum flexural tensile stress in the beam. Simply we use the equation tensile stress maximum is equal to my, in this case now, y max all over I, where m stands for the moment, y max stands for the what? The neutral axis or the point of the maximum flexural strength, and I stands for the moment of inertia. Okay, so where I, which is the moment of inertia, is given as b h cube all over 12. Okay, I is simply bh cube divided by 12. So this implies that I is equal to b was given in the equation as the width. So we are going to be solving with the values in meters, which is 0.11 meters. So we have 0.11 multiplied by h is the depth, which is 0.24 all cube divide by 12. So I will point the whole of this at once to obtain a value. So you do well to also point the values together to ensure accuracy in the calculation. So the whole of this gives me 1.2672 by 10 to the power of minus 4 in meters 4. All right, so that becomes the moment of inertia for a rectangular section. Please take note, this is moment of inertia for a rectangular section. Since it was stated here that this is a rectangular section, you have that. Okay, now the problem now is how do we find moment, because we already know the neutral axis or the point of maximum flexural strength. We already know this value y max. How do we then find the moment of the moment m or the bending moment? So you consider the beam. Okay, to find the bending moment, moment is simply what the load itself, the load carried P multiplied by the length of the beam. The load carried multiplied by the length of the beam. So let's fall back to the beam. The beam gave us L1 to be equal to 2.4, L2 to be equal to 3.5. If we add them all up, 2.4 plus 3.5 gives us the entire length of the beam, which is 5.9. And the load P was given equation as what? 84 kilonewtons. So this is actually what? P is 84, kilo is by 10 to the power of 3 times L. Total length becomes what? 5.9. So you have this. So this simply means that the moment is equal to, let's obtain now, 84 exponential 3 multiplies 5.9. 495.6 by 10 to the power of 3 newtons meter. All right, so we have this to be the moment. If you have this to be the moment, you can plug into this equation now. Therefore, sigma max, which is the maximum flexural stress, is now equal to moment 495.6 by 10 to the power of 3 multiplied by y max. Y max simply gave us 120 millimeter. So you convert this to meter by dividing through with 1000. You are going to have 0.12 in meter. So multiply by 0.12 divides by I, and we obtain I to be this. Okay, we obtain I to be this 1.2692 1.2692 by 10 to the power of minus 4. So I'm going to punch all of this together as well to obtain the value of that maximum stress, just to save time. All right, so everything gives me approximately 4.69 megapascal. So we have punching everything together, I have approximately 4.69 megapascal for the maximum stress. Okay, guys, so that's it on that particular question. I hope you find this video very interesting and helpful. Please, if you do, I would like to get your thoughts in the comment section. Like this video, share to your friends, and of course, if you're new to the channel, do well to subscribe to keep getting updates when content as this drops. I will see you in the next video. Thanks and cheers.